Good morning, students. Can you all see my screen?
Yes, madam.
Okay, right. So I hope you all have gone through the recordings which I have uploaded in last week. So there, I have discussed about the multiple linear regression, and in multiple linear regression, we know when you take the simple linear regression and compare it, the difference is we have so many variables when it comes to multiple linear regression. But in simple linear regression, we have only one x variable. So in that case, when it comes to real world problems, when you have so many x variables and when you are asked to fit a regression line, in that case, we should be able to pick the most important x variables. So in the last session, I have discussed how to pick the most important x variables using extra sum of squares. So in that case, you can use the extra sum of squares. That is, for an example, you can, if you have three x variables, x1, x2, and x3, what you can do is you can fit a regression model using x1, x2, and x3, and then you can obtain the Anova table. And then if you want to check whether x2 is important, let's say, whether x2 is important, then what you have to do is we have to again consider a model with x1 and x3 without x2. So then you have two models. In the reduced model, what has happened, you have x1 and x3, and in the full model, you have x1, x2, and x3. So in that case, we can check whether we are going to use the reduced model with x1 and x3, or we are going to use the full model as x1, x2, and x3. So you have to take the extra sum of squares and conduct the hypothesis. So if you look at this example, so it's about a recent survey which have been conducted using a sample of employees of a financial organization. So they want to check the satisfaction, employee satisfaction with the supervisors. So they have taken Y as their response variable, and Y is the overall rating of job being done by supervisor. So there are so many x variables. You can see there are 6 x variables. X1 is handles employee complaints, x2 is does not allow special privileges, x3 opportunity to learn new things, x4 raises based on performance, x5 too critical of poor performance, and x6 is this should be rate of advancing to better jobs. So in this case, so you can see there are so many x variables, and we are supposed to build a regression model using these x variables. So in this case, sometimes when we fit the model, we will see all the x variables are not that important. So in that case, we can select some of the x variables and develop our model. So if you are supposed to build a multiple linear regression model like this, now in this case, actually you have, this is the data set. Here you have 30 observations. So if you are supposed to fit the multiple linear regression, you can use the matrix form, right? We have discussed one example using the matrix form. So you can use this one, x transpose x inverse x transpose y. So you can just obtain the x matrix, and you can obtain the y matrix, and then you can do the calculations just as we have discussed in one example, and then you can obtain the coefficients. And then what you can do is you can just check if you are using the t-test, you can check for one by one coefficients whether these coefficients are significant or not. right? You can conduct t-test for that. So in this case, if you just fit a multiple linear regression model, you will see this is the equation that you get. Or else you can use a statistical software. You can use R in order to fit the regression model. So I will show you now how to fit the regression using R. So in that case, so if you're going to fit the regression model using R, first what you have to do is, I have already taken this data set and I have saved my data set as CSV file. I have copied my data set into an Excel sheet and I have copied it as an Excel file. So now first thing in R, we have to import our file to R. So for that, we can use first I have to give a name to my data set. Let's say my data. Then I can use read.table command, and within brackets I have to use file.choose, comma, header equal true, comma, we have to separate all the values using, and here sorry, here file.choose should be dot. So when I call this command, I can choose my data set. Here I have saved my data set as an Excel sheet, as a CSV file. So I'm going to select my data set. And I will just call my data and see whether I have imported my data set correctly. So you can see my data set has been imported. So if you just check the columns, you can see in the first column you have my data set's name is my data, and I have used the dollar mark, and my first variable is x1. So I just check whether I have imported all the values correctly. So in this case, if you want to fit the regression model, first you have to give a name to the regression model. So I will call it as fit1. So as in linear regression, we are going to use the function lm, and then first you have to give your y variable. So in this data set, you have a variable called y. So I'm going to set it as my y variable. And then I'm going to use my x variables. Here I have 6 x variables. So x1 plus x2 plus x3 plus x4 plus x5 plus x6. So I have to include all the x variables, and all these variables are coming from data set my data. So I have to give the name data is equal to my data. That is the name of my data set. Now I have fitted my multiple linear regression model just to check whether just to check the coefficients and everything. I can just call the name of my regression, that is fit1. Then you will see the intercept and the coefficients of all other x variables. And also, if you want to obtain more summary of this fitted regression model, we can use fit summary, and within brackets you can give the name of our regression model. Then you will see a summary of your regression model. right? You can see the intercept is 10.78, x1 is 0.61, x2 is minus 0.73. Likewise, you can see all the outputs here, all the coefficients of the x variables with the intercept. And if you want to obtain the Anova table, that is also can be done. So the command is just as in simple linear regression, you can use the function, built-in function Anova, and within brackets you can give the name of your regression model. So in my case, that is fit1. So here you will see the regression model. I will just copy this regression model because there is more difference between the output and the exact regression model that we are going to construct. Anyway, you can take all these outputs using R, even when it comes to multiple linear regression. So now let's compare with our note. Okay, so we saw when we fitted our regression model, our intercept was 10.7 and the coefficient of x variable was 0.613. So this is exactly the same. So we can see when it comes to our regression model, all the coefficients we can obtain using R software. And also, I'll just paste the output of yeah. Okay, so this is the Anova table output. In this case, you can see if you just check out the significance of the coefficients. In this case, you can see if you take x1 variable, you have this code here that is it's significant with 0% of significance level. And when you take this x3 variable, that is also significant with 0.1 level of significance, because there are two arrows here. I have not copied that. So anyway, when it comes to this regression model, as for the output, we can see only two variables are significant, that is x1 and x2. So if you want to decide whether you are going to actually keep only x1 and x3 in model building, what you can do is there are two steps that you can follow. If you want, you can check for the significance of all these parameters one by one using the t-test. That is, you can check for beta 1, beta 2, beta 3, likewise by conducting the t-test. Or else you can use the extra sum of squares as well. Right? Now in this case, when it comes to so when it comes to the Anova table, in multiple linear regression, we discuss it's the same as the simple linear regression. So you have the regression, residual, and the total. We have to include the sum of squares, and we have to include the degrees of freedom, mean squares, and the f-test. So in this case, let's say, now, since we have beta 1, beta 2, beta 3 up to beta 6, if we want to check whether these, whether to include all these coefficients, whether all these are equal to 0 or not, we can use extra sum of squares. Now, if you just check, this is the Anova table of the full model. So if I just compare this Anova table with the computer output, now you can see in the computer output, we have the residuals and the degrees of freedom is 23. So this is the Anova table of the full model we got from R. So when it comes to residuals, we have residuals, degrees of freedom is 23, and the sum of square value is 1149. So if you just check it with the output, that is correct. 1149, and then mean square is 49.96, so that is also correct. And then when it comes to the regression, you can see when you look at the computer output, we cannot see anything like regression. but we can see all the independent variables here. So if you are going to construct the Anova table manually, what you have to do is, after taking the computer output, in order to take the values with respect to the regression, you have to take the total of all these independent variables. Now, in this case, you can see you have 6 independent variables. So if you take the total of all these 6 degrees of freedom, since you have 6 independent variables, you can see it's equal to 6 degrees of freedom. And you have to take the summation of all these 6 sum of squares values, and then you will see that is adding up to 3147.97. And then it's same as the mean squared values. You have to add all these 6 mean squared values to obtain this mean square. And in that case, we can, after obtaining the regression, the residual, then total, we can just take the total of the regression and residuals. And then the mean squared values also we can take by dividing the sum of squares by the degrees of freedom. So we can conduct the F test. And in this case, now let's, I'll just remove this. Yeah, now imagine, now we want to check whether all of these parameters are equal to 0 or not. So in this case, if all these parameters beta 1, beta 2, beta 3 up to beta 6, if all of them are equal to 0, we know our in the reduced model, we can include only the intercept. So we can come up with a reduced model that is y equal beta naught with only the intercept. And in our full model, we can take beta naught plus beta 1 x1 up to beta 6 x6. So if this is the full model that we have obtained, for the this is the full model, this is the Anova model of the full model. And in this case, what you can do is, we actually discuss in when it comes to extra sum of squares, if you look at the full model and if you conduct the F test using the Anova table of the full model, this is the hypothesis that we use to test. That is, with the use of only the full model, we take the reduced model with only the intercept and the full model with all the possible x variables. So we can see here the F value is 10.5. So in this case, we know here in this case, the F value is obtained by dividing the mean square error and the mean square regression. So in this case, if you check the respective degrees of freedom, the mean square error degrees of freedom is 6 and the mean square regression degrees of freedom is 23. So we have to check the table F value with the numerator's degrees of freedom is 6 and the denominator's degrees of freedom is 23. So in that case, here if you take 1% level of degree, 1% level of significance, you will see the table value is 3.71. And you can see here the F test value is 10.5. So the calculated value is greater than our table value. That is, we can reject H naught. So we are rejecting H naught is we are rejecting the reduced model. So that is, we can conclude, since we are rejecting the reduced model, we can conclude that all the coefficients beta 1, beta 2 up to beta 6, they are not equal to 0. There exists at least one parameter which is not equal to 0. So that is what we can conclude here. And in this case, what will happen now when we fit the full model with all the regression, all the independent variables, and when you just check whether the parameters are equal to 0 or not. And when we can just conduct the t-test individually for each and every parameter. So what will happen here is, sometimes when you just check the significance of each and every parameters individually, let's say all the parameters are becoming significant. In that case, when you conduct the F-test using the Anova table, you will easily get the conclusion that all the parameters are not equal to 0. That is, parameters are significant. But in some cases, when we conduct the F-test, when we conduct the T-test individually for the parameters for beta 1, beta 2 likewise, then the parameters are becoming, they are not becoming significant. Right? For an example, when you conduct the T-test for beta 1, it's not significant. It's equal to 0. So if your situation is when you conduct T-test for each and every parameter in the model, if you can conclude that beta 1 equal to 0, beta 2 equal to 0, likewise up to beta 6 equal to 0. But if you just take the Anova table again, and then if you use the F-test and conduct the significance, then when you check the significance of the model again, sometimes you will see the F-test is significant. That is, from the F-test, you are rejecting H0, and then you are saying at least one beta coefficient is not equal to 0. But when you conduct the T-test individually, all are equal to 0. So there is a contradiction. That is because sometimes when you take the individual coefficients, they are not significant. But when you take them together as in a linear relationship, that will be able to explain the variation of this response variable. That is why it's becoming significant, even they are not individually significant when you conduct the t-test. So that is something possible. So actually this thing is happening when there is interrelationships between your x variables. Now, when it comes to regression, we want to see a very good relationship with x variables and y variables. But there are some situations where you can see there are correlations among x variables. For an example, x1 and x2 are related, x3 and x4 are related. Likewise, we can see relationships among x variables as well. So this concept we call as multico-linearity. And we'll be discussing about this later. So when you have this multico-linearity, we can see when you check for the significance of individual coefficients, they are becoming insignificant. But when you take all the independent variables and when you fit the regression model and when you check it with the Anova table, it's becoming significant. So that is the reason. And in this case, we saw that when we got the output from R, when we fitted the model, we saw that only x1 and x3 are significant. So we can actually, you can just conduct the t-test and check whether x1 and x3 are significant or not. And here, this is the Anova table that they have used by fitting the model using x1 and x3 variables. So this is actually the reduced model. So you have only x1 and x3 variable, and this is the Anova table. And we have the Anova table for the full model as well. So in this case, actually we can conduct the extra sum of squares. So now we'll just write the extra sum of squares, let's take the extra sum of squares in regression. So in the first model, we have x1 and x3, and in the full model, we have all the variables. So that is, at the beginning, we have x1 and x3. So given that x1 and x3 are in the model, we are going to add the other variables into this model. That is, we have to add x2, and we have to add x4 and x5 and x6. So this is the extra sum of squares, which is related to these two models. When it comes to the full model, you have all the variables. When it comes to the reduced model, you have x1 and x3. So in the last lecture, I discussed how to write the extra sum of squares. So x1 and x3, they are already in the model, and we are going to add x2, x4, x5, x6 to convert this into the full model. So the difference between the error sum of squares or regression sum of squares are known as the extra sum of squares. So in this case, if you take the regression sum of squares, here you have this value. And if you take the full model, here you have this value. So we know when it comes to the full model, and when you observe the regression sum of square, in the full model, regression sum of square is a high value, because when you have so many x variables, it can explain the variation of your y variable. The accuracy of explaining the variation of your y variable is high when you have so many x variables. So the regression sum of square is a high value when you have many x variables, right? But in the other way, when it comes to the error term, when you have only few variables, error is high. Here, if you look at the residual sum of square, it's 1149. But if you just check the error sum of squares here, it's 1254. Here the error is a big value compared to the full model. So you can take the difference between these two, that is the extra sum of squares difference. And in that case, that is 3147.97 minus 3042.32. So that is adding up to 105.65. So this is the extra sum of square. And then we can actually calculate the F value. So the F value, how do you calculate? First, you have to take this extra sum of squared value, that is in our case 105.65, and here you have to divide this by p plus 1 minus k. What is p plus 1? P is the number of independent variables in the full model. So in our case, you have 6 independent variables in the full model, and p plus 1, that is equal to 7 then. K is the number of parameters in the reduced model. So in the reduced model, you have only 2 x variables, and with the intercept, you have 3 parameters, beta naught, beta 1, and beta 3. So K, in our case, K is equal to 3. So that is P is 6 and K is 3. That is 6 plus 1 is 7. 7 minus 3 is 4. So this one you have to divide by 4. And then you have to take the full model error sum of square value, and that is this one. When it comes to the full model, you have to take the error sum of square value, and then you have to divide this by that error sum of square divided by n minus p minus 1. So in our data set, we have 30 observations. P is 6 minus 1. So 30 minus 7, that is 23. So this one again you have to divide by 23. So when you take the ratio between these two values, you will get the F value, the calculated F value. Just we'll check. The numerator is 26.4125. And if you divide 1149 by 23, that is 49.96. And then 26.4125, you have to divide by 49.96. So that is 0.528. Right? So you can see when it comes to this value, when you conduct the F test, here you get the value as 0.528. So now we can compare this with the value of the table value of the F table. So we have to check here the degrees of freedom is 4, the numerators, and the denominators degrees of freedom is 23. So if you just check with the 5% of 5% level of significance, you will see the table value is equal to 2.8. And we can see here the table, when you compare the table value with the calculated value is less than the table value. So we don't have enough evidence to reject H naught. That is, we can't reject H naught. We have to come up with the full model. We can't use the reduced model. That is, we do not have enough evidence to reject H naught. That is, we have to accept H naught. That is, we have to accept the reduced model. We can't come up with the full model because H naught is the reduced model is the good one, and H1 is the full model is the good one. Since we are not rejecting H naught, we can come up with the reduced model. So that is, we can only use X1 and X3 variables in our regression model to do the predictions. That will give you a more accuracy than using all the variables. So likewise, you can check what are the variables that you have to include in a given model when you have so many X variables. So just as in simple linear regression, after you fitted your regression model, we have to check the accuracy of your regression. So before talking about the accuracy checking, do you have any questions up to that point? If you have, you can ask. I hope you go through all the videos, the 2 videos that I uploaded on Monday. Sorry, on Tuesday. Okay, so if you have no questions, because if you have not gone through the videos, I'm sure that you will not understand what I'm saying today, right? So you have to go through the videos. And in this case, here, as I explained you, now we know how to fit the regression model. We can use the matrix form, or you can use the computer software and import your variables, and then we know how to fit our multiple linear regression model, and we know how to find out what are the important variables. And then we can just keep those variables in our regression model, and we can remove the others, and we can come up with a good regression model. So after we conclude that this is our regression model, we have to make sure we have to do some of the testings. So when it comes to simple linear regression, we check for the assumptions of the residuals. No, we check whether the residuals are normally distributed, whether the residuals are having the constant mean value. So same process you can do with the multiple linear regression as well. So I showed you how to take the outputs when it comes to the simple linear regression in R, how to take the residual plot. So the same plots you can take when it comes to the multiple regression. So I'm not going to explain them. So you can use the Cook statistics as well in this, even with the multiple regression. But apart from that, there are another 2 important plots that we can obtain when it comes to multiple linear regression. So one is the added variable plot. So in added variable plot, what we do is, if you want to check, now for an example, now in the data set that we just discussed, we had 6 variables. So if we want to check whether X1 is really important or not, we can use this added variable plot. So in that case, what you have to do is, in the added variable plot, first we take the variable that we want to check whether that variable is important or not. First, you have to remove that variable from the full model. So if you are going to check for x1, what you have to do is first you have to remove x1 from the full model, and then you have to fit a regression model using the other variables. For an example, you take y and we fit a regression model using x2, x3, x4, x5 and x6, because we are going to check whether x1 is important or not. Right, we are going to check whether x1 is important or not. In that case, we remove x1 and we take y, and we remove x1, we take all the other variables, and then we are going to use these variables and fit a regression model. So after fitting the regression model, what you have to do is you have to obtain the residuals of this one. We remove the variable that we want to check. We fit a regression model with all the other variables, and then we obtain the residual plot. And then what you have to do is you have to take the removed variable that you want to check, that is x1, as your y variable. And then you have to fit a regression model with all the other variables, all the other independent variables, that is x2, x3, x4, x5, and x6. And then again, you have to obtain the residuals. Right? And then what you have to do is, now you have two types of residuals. Then what you have to do is you can just use a plot, and as your x variable, you can take the residuals which are coming from this model. That is, you have taken x1 as your response variable. So I'll take it as these residuals. Let's take it as xr, and these residuals, let's take it as yr. So in a plot, you have to give as your x-axis these xr values and these yr values as y-axis and plot it. So that's how you obtain this added variable plot. So actually, if there is a good relationship among these two residuals, that is, this x1 variable is really important, we have to include that in the model. So we can just check this in R. I will show you how to obtain this plot in R. Right, so in R now, since I have my data set, we have already imported my data here. Now in this case, I'm going to check whether x1 is an important variable to include in the model. So I'm going to take, now already I have all the variables. So first thing that I'm going to do is I'm going to remove x1 from my model and fit a regression with all the other variables. So first I will give a name to this regression model. Let's say fit2. And here what I'm going to do is I'm going to fit a multiple linear regression model where y is my response variable. And I'm going to remove x1. And I'm going to use x2, x3, x4, x5, and x6. And these data are coming from my data set. So this is my regression model. So if you want, you can just call fit2 and see the coefficient. So you can see I have the intercept. and only x1 is missing. All the other variables are here. So what I'm going to do is I'm going to take the residuals of this fitted model. So I will store those residuals as y residuals. So in R, there's a built-in function called residuals. So you can just give the model here, fit2. Right, so the built-in function residuals you can use. So what I have done here is I want to obtain the residuals of this linear model fit2. So the built-in function is residuals. So within brackets, I have to give the name of my fitted model. So that is fit2. So now if I just call these y residuals, you will see you will get 30 residual values. So now I have stored all these residuals to y residuals variable. And then what I have to do is I have to fit another regression model. So I'll take it as fit3. What I have to do here is, in this case, the variable that I removed from the model is x1. So I have to take x1 as my response variable and all the other variables as my independent variables, that is x2, x3, and x4, x5, and x6. And these variables are coming from my data set. CR is very case sensitive. So you have to, when you are giving the names, you have to give them very precisely, otherwise you will get errors. Now I have this fit. If I call fit3, you can see again I have the intercept and the other coefficients of the x variables. So here also I want to store the residuals of this model separately. So I'm going to do, I'll take x residuals as the name, and then I'm going to use residuals built-in function. And here the name of my regression model is fit3. So now I have stored the residuals of this model. So you can see I have 30 residuals. So in this case, I can obtain the plot, the added variable plot. So I can obtain the added variable plot of these two. So what here I can do is, as my x-axis, I have to put the residuals, which I obtain using x1 as my response variable. So in my case, that is x residuals. And my y-axis is y residuals. Yes, see, I have used simple case letters for residuals. That's why there's an error. So here I can use these two residuals. Yeah, so here when you give the two residuals and when you fit a scatter plot using these two residuals, let's observe the scatter plot here. This is the added variable plot. So in this case, if you really want, if there's a strong relationship between these, now when you look at this plot, we can actually see there is like a linear trend. But in order to clarify that, you can actually just check the correlation also between these two variables. So I'll just check the correlation of the two variables. So you can see the correlation is plus 0.621. So that is, there is a moderate a positive correlation value. So that is, we can just say X1 variable is important. When you add that to the system, it is something important. So likewise, for each and every variable, you can just obtain this added variable plot and check whether it is important to add to the system or not. And this is actually the codes that I showed you right now. That is how to obtain the added variable plot manually by using our own codes. But in R, there are built-in functions that you can use to obtain this added variable plot. But if you just search and if you just try to use those built-in functions in order to obtain those plots, sometimes you may not be able to use those functions, because sometimes to execute some of the functions, we want to import and load some of the packages to R. So without the use of that package, we cannot actually use this those functions. For an example, there is a function called AV plot. So AV, with the use of AV plot, that is added variable plot, you can, when you just give the model and the variable, you can nicely obtain the added variable plot using R. But if I just use here, I'll show you, if I use this AV plot, and let's say I give fit to X1, you can see I will get an error saying AV plot function is not here in R. That's because the package that which consists this function, it's not coming with the default version. We have to install that. So to do that in R, what you have to do is you have to go to package, and then you have to go to install packages. So when you go to install packages, if you're going to this install packages for the first time, now in my case, I have installed packages earlier. So if you are going to install packages for the first time, here in this pop-up window, you will see a list of names of the countries. So in that case, you can select India or Singapore and select OK. And then you will see this list of packages. So in this case, to get most of the plots related functions, we have to use the ggplot. There's a package called ggplot. So I'm going to install that ggplot package. So in the packages list, you have to find out the name of the package that you want to install. Yeah, so ggplot2, this is the package that I'm going to install. So you select that package and press OK. So then R will automatically install that package to your version of R. So it will take some time. So you can do it in this way, or else what you can do is when you're installing the package in this way, that the important thing is now when you want to install package ggplot to R, if the package ggplot needs some other packages to be installed prior to this one, R will automatically install all the packages. Or else what you can do is you can just download the zip files of these packages. They are available on Google, so you can just Google and download them, and then you can manually install them as well. But if you manually install them, what will happen if you only download ggplot and if you only install that, when you try to run it, sometimes you will not be able to run that because you need some more packages to be installed prior to that. So then you have to download all the other zip files as well. So that is something which is time consuming. So this way is easier, but you need to have a good internet connection in order to download these packages. So yeah, so after downloading all the packages, still my okay, so I'll let it be like that. So after downloading, you will see when it's done, you will see the cursor will come to the next line. So what you have to do is you have to go to packages, and then you have to do load packages. You have to go to load packages and select ggplot2, the package that you installed right now. Or else what you can do is you can just type, I'll just keep this one as it is, and yeah, after you're done with the installing part, what you can do is then you will see what you have to do is in the console, you can just write library and within brackets the name of the package that we installed. So in our case, that is ggplot2. Library is simple. So if you just run this, then we have load the package to R. So then we can use all the functions with related to this ggplot to obtain the output. So in that case, you can use the avplot function as well. So that is for homework. Just check whether if you want to use a built-in function to obtain these plots, you can just check what are the available packages in R, and you can install them, and then you can just try with the built-in functions. So the other thing, when it comes to now, we know if you want to check the important, if you want to check whether a particular variable is important, when it comes to multiple linear regression, we can use this added variable plot. So there's another plot which is known as the residual plus component plot. This is actually used as a graphical method in the at the very early stage of statistics in regression analysis. So in this case, what you have to do is, now if you want to check whether xj, let's say any response variable is any independent variable is important. So let's say we are going to check the importance of the variable xj. So what you have to do is, in this case, you have to take the scatter plot between xj and e plus beta j xj. So what is this e? E is the residual that is when you regress your response variable y with all the predictors, we can obtain the full model and we can consider the residuals. Those residuals are known as E here. And when you regress the full model, there is a coefficient which is related to this xj variable. That coefficient is known as beta j. So you take that residual plus beta j times xj as one coordinate and the other as xj. And then you can obtain the plot. So in this case, when you obtain this plot, we can again check whether this adding this xj variable, if there's a good relationship between these two variables, whether that is an important variable, and also if this plot seems to show non-linearity, non-linear relationship, that is, it's not good. There is we can check whether it's good to go for a linear relationship with these variables with the use of this plot. So that one you can just give a try, but now we have already fitted the full model, so you can obtain the residuals. So what you have to do is we can just check the coefficient of the full model. And then we can take the residuals plus the coefficient times x and store it into another variable. And then you have the xj variables, and then you can check what will happen. You can obtain the plot and say. So in this case, so just now we discuss when you have so many variables, we want to know what are the important variables to be added to our multiple linear regression model. So actually, in general terms, the questions that we have when you have so many x variable is the regression coefficient of the new variable is significant? If we are going to add a new variable to our system, when we are fitting the multiple regression model, one thing that we have to know is whether the coefficient of this new variable is significant. And also we have to check when we add this new variable to the system, what will happen to the coefficients of the other variables which were already in the system. Are they changing or not? So this one we have to check. So what we do is now when we are fitting a multiple linear regression model, actually, when we are adding variables, let's say initially we have fitted the regression model with the use of variable x1 and x2, and then we add the variable x3, and then we check whether the coefficients are changing or not. So one possible case is when we add a new variable, the new variable might be insignificant. Right, new variable, it can be insignificant, and also the remaining regression coefficients, they will not change. So in this case, we have no problem. We can just exclude the new variable if we do not have any other external condition. So we can remove that variable because it is insignificant when you add that to the system, and also the coefficients are not changing. So in that case, yeah, so I don't want, thank you for the message. I don't want your student numbers. I recorded all the list of participants, so I do not want your student numbers today. Thanks for the message. Anyway, now, when you add this variable, if the variable is not significant and the other coefficients are also not changing, then you can exclude the variable from the system. But sometimes what will happen is when you add a new variable to the system, that the coefficient of that variable, it may be significant. And also what will happen, the coefficients of the other variables, they will also change. So in this case, this new variable has an impact on the regression. So we can't exclude that. So we have to keep it in the system. But in this case, this is actually a sign that the sign to say that there are relationship between the X variables. Right. So in such case, what we can do is we have to actually check whether the X variables are interrelated. So that is known as the multico-linearity, which we'll be discussing later. So we have to check whether there is multico-linearity. Then we have to use the techniques that we have to come up to overcome this multico-linearity. But in that case, we cannot remove the new variable because the new variable is significant and it's also changing the coefficients of the other remaining variables in the system. So we can't exclude that new variable. And sometimes when we add the new variable, that is significant, but the regression coefficients of the previous introduced variables, those things will not change. So this is the ideal situation. This is the perfect situation that we really expect, but it's not happening most of the time. So if that is the case, you can keep your new variable and the multico-linearity is also not there. So we can fit the regression model with the new variable with no problem. And sometimes when you add a new variable to the system, the new variable will be insignificant, but the regression coefficients, the regression coefficients of the previously added variables, they will be changed. So in this case also, that is clear evidence for multico-linearity. We have to take the possible and appropriate actions to overcome the multico-linearity. That is, there are relationships in between the X variables. So these things, what is multico-linearity and how to overcome the multico-linearity, we'll be discussing it in the coming lectures. So when it comes to the prediction purposes, now when you fit the regression model in multiple linear regression, it's just same as the simple linear regression. If you want to predict the values, you can just substitute the values to the equation and then you can predict them. Now here, if you look at this one, this regression model, we have come up with this fitted equation. Y hat is equal to 10.78 plus 0.61 x1 minus 0.07 x2 plus 0.32 x3 likewise. So if you have a set of x variables, let's say x1 is equal to 10, x2 is equal to 25, x3 is equal to 65, x4 40, x5 55, and x6, let's say 24. So if you want to predict the value of y for these values of x variables, then you have just simply you have to substitute the values to the equation. So you have the intercept as 10.787 plus 0.613 into x1 value now 10 and minus 0.073 into x2 value is 25 and 0.32 into x3 is 65 and 0.081 into x4 is 40 plus 0.038 into x5 is 55 minus 0.217 into x6 is 24. So just like this, we can just substitute the values to this equation and do the predictions. It's same as the simple linear regression model. You can do the predictions. Okay, so do you have any questions up to that point? So if actually in the exam, if I ask you to fit the multiple linear regression model in the exam, you will not get so many X variables because it's not possible to do the calculations using the matrix form with all these if you have so many X variables, but let's say you have 2 X variables, then it's possible, right, to fit the multiple linear regression model with the use of the matrices. So that one you have to be familiar. Okay, we have already discussed one example how to use the matrix format. So you should be able to do it manually as well when you have maximum up to 2 variables. Or else we can always use a computer software when we are solving questions in real life scenarios, but in the exam you should be possible to use the concept of the matrices when you have maximum number of 2 X variables. Yes, so do you have any questions? Okay, so if you have no questions, I'm going to stop from this point for today, and we'll meet again on Tuesday. Thank you so much, and have a good day.